Okay, we'll just try to wrap up the next part. So before we head to which prologue, what we want to do is define a bit more formally what different kinds of learning are, and basically tell you what we have done in a bit more formal way, but less technical. So one of the things here is we need to define the notion of data presentation to the learner. The learner is learning this concept. We have seen possible evidence which is being presented to the learner. So we define, given a model M which belongs to the class we have selected W, an environment for M is an infinite enumeration of the members of the diagram for M. That is, you take all the elements in the possible state which are true in the model, and then if you take an infinite enumeration of those elements, what you have is an environment. And the idea here is that eventually every data is going to be made available to the learner. It's just that learning doesn't have to wait for the infinite set of data to be available. Learning is something that's an ongoing activity. Data is being made available one by one, and at some point learning has taken place. So the environment basically models data presentation. So how do we define learners? Given an infinite sequence E and a number k, by E of k we denote the initial segment of E of length k. So E of k is basically the data that is available at any given time to a learner. So E is the environment. It is the potential abstract infinite sequence of data. But the machine is not going to operate on an infinite sequence of data. It is only going to operate on a finite segment of this. And E of k denotes the initial finite segment of length k. Then another notation, given a partial function f from x to y, where x belongs to x, we write that f of x is defined like this, down arrow, if f of x is defined, and f of x up arrow if the function is not defined. It's just for some technical convenience. Then we define a learner. A learner is a partial function from the set of finite initial sequences of members of E into 0, 1. So the idea is that finite initial sequences of members of E are being presented, and the learner has to output 0 or 1. And the idea is eventually, if it is learning in the limit, it will converge to 0 or it will converge to 1 if the formula phi that it is trying to learn is true in the underlying model or not. And of course there are certain other cases because it doesn't have to always converge. The first notion is a finite learning. In finite learning, what you do is basically you keep looking at the data and keep holding back your conjecture. But at some point you have seen enough data and then you say, this is the answer. Now, this is also called one-shot learning. That is, you do not get more than one chance here. You are allowed to wait for as long as possible to convince yourself, but eventually you have to output and that's it. Whereas in other notions of learning, you may be allowed to output a current working hypothesis, but if the data conjectures, the new data that you get actually says that this is not the case, you are allowed to actually conjecture something else. And depending on how many times you conjecture, the complexity of learning increases. Okay? So, given a learner f and a formula phi, we say that the learner f finitely learns phi if and only if for all models M from the class of concepts W that we have selected, and environments E for M, which is E is the sequence of data that are true in M, the following are equivalent. If phi is true in the model, then the learner F must converge, and it can converge to 1. In this case, it cannot converge if phi is not true, but so it doesn't really have to converge to 0 or 1, it just has to converge to something. So if the formula phi is true in the model M, then the learner F, after seeing enough information, must converge and say yes. Okay? If it is not true, then it doesn't have to converge. The second game is a particular case of finite learning. So in the second game, what we have were all the Herbrand models of the background knowledge and the thing that said only those structures are taken into account which allow 1 and 2 before 0 in the in the order. And the data available, the possible evidence, was the predicates of the form before mn. So some learner can finitely learn the formula for all x before 2 of x. That is, 2 is before x. Okay? So what we did there was simulate a finite learner. The next complicated version of learning is called refutation learning. This is where actually induction takes place. What you say now is that I am able to say that a for all x p of x kind of a sentence is true in the model, in the sweet confidence that if it is not the case, I will get a conjecture, and then I'll be able to say it is not the case. So this is something that we just have to do. Like, we see enough evidence of something, and then we say all these things must be of this kind. This is a fundamental step in induction that we have to do, but we are not as sure as we are in deduction. So given learner f and formula phi, we say that f refutably learns phi if and only if for all models from the class of models or the concept that we have selected and all data environments E for M, the following holds. If the formula phi is true in the model M, if the formula phi is true in the model M, then the learner f outputs 1 for all k equal to n. So if it is true, the learner n right away from the GRO says this formula is true. If the formula phi is not true in the model, then there exists some point k such that the learner would have output 1 for up to that point, but after that it must output only zeros. Okay, it's a very common sense kind of a thing. You have to conjecture a for all x sentence. For all x, some formula is true or not. You go ahead and conjecture unless the first data that you have seen contradicts it. In this case, you can say that this formula is false right away. But you go ahead and conjecture it, and after a while, if you see that something is contradicting it, you just say, no, it is not true. Okay? You might say, why it makes, why is it interesting? Well, the idea is, whenever you do induction, you have to make a jump like this. Because you will never have enough data to convince yourself that the induction that you have performed is actually going to be correct. You have belief in it, and you hope it is right, and you hope that the contradiction will not happen. But that's all you can do. So the third game is a particular case of this. W, the class of all Herbrand models of BK, and E is the data set that we have, all the symbol, all the literals of the form before Mn. So some learner can refutably learn the sentence for all x such that 2 is before x. And when we did the third game, we actually simulated that learner, and it was a very simple learner. Finally, learning in the limit. Given learner f and formula phi, we say that f learns phi in the limit if and only if for every model M in the class of concepts or models we have selected and for the environment E for M, the following are true. If phi is true in the model M, then the learner f has to output 1 for all but finitely many k. That is, for the first few sets, a finite number of times, it is allowed to output 0, 1, 2, whatever, it can output 0 or 1 because we have restricted f to only output 0 and 1. It can output 0, 1, it can vacillate between 0 and 1, but eventually it must output and converge to 1 if the formula phi is true in M. Okay, and this is the standard notion of learning in the limit. The fourth game was the particular case of this where we had W to be the all Herbrand models or the background knowledge K, that was the set of axioms, and the extra requirement that either it is, if it is having a minimal element, it doesn't have a maximal element, and the data was almost the same as what we have been having before. Then the learner that we simulated was able to learn there exists x for all y before xy. While I was explaining that thing, I realized that, like, there was I jumped one step further. So when you put the notes on the web, you can go and simulate it again and find out. The 4 games apply inferential mechanisms that derive statements from other statements and discover the truth. So basically what learning does is you have a set of statements, the set of axioms and the data that is available, and based on that you determine whether a formula is true in the underlying model or not. This is also something that you do in deduction. So the point here is that if we have a mechanism for deduction, why we don't have a mechanism for induction? And what we are saying is that if we make certain generalizations of classical logic, for example, restricting it to the class of Hilbert models, there is a beautiful and elegant theory that actually allows us to cast deduction and induction in the same framework. And this is the point of this whole thing. So 4 of them are in the realm of logic. Classical logic is a particular class of such games that we have seen, and discovering the truth can pose various degrees of difficulty. Okay? Truth classified as easier to discover. They are the truths that can be discovered by finite learning. That is, they're simple classes. All you got to do is wait for enough data, and then you'll be able to tell whether that formula is true or not. These are same as the truths that can be discovered by deduction in the revised sense, where we restrict it to only Hilbert models. In classical logic, all truths can be discovered by deduction. Truths with difficulty possess the next level of the difficulty. These are the truths that can be discovered by refutation learning, and these are the truths that can be discovered by induction. That is, here we make an inductive leap and say that for all x, some formula is true. Truth whose discovery poses the next level of difficulty. These are truths that can be discovered by learning in the limit, truths that can be discovered by induction followed by revisited deduction. Truths harder to discover are in the realm of logic but not in learning. Now it turns out that there is further generalizations of these things. You can actually have infinitely more complex levels of learning that you can take place, but it is extremely difficult to give an intuitive meaning to what is going on. So only the first 3 levels seem to actually look like learning. Just a very small point here. A lot of you have been attending the machine learning workshop, and you probably have been exposed to the PAC paradigm, and you might actually see, where does the PAC paradigm fit into all these? Well, actually PAC paradigm is a special case of finite learning. Okay, it is like finite learning, but it is a restricted case of finite learning. And here is the difference. In finite learning, what happens is that you are allowed to basically, you just have one shot at the answer, and that's how you do in PAC 2. You just have one shot at the answer. But in finite learning, you are allowed to look at enough data, whereas the criterion for PAC says if a certain data bound has been achieved, your answer must have certain properties. Okay, so that is a subtle difference that is important here. PAC is a special case of finite learning in the probabilistic setting, but finite learning is somewhat more general because you're allowed to actually see more data than like in PAC, because PAC actually, the definition itself has a data bound included there. And all that can be cast in the logical framework. It's a very general framework, but it's going to take some work. Okay, so the 4 games are in the realm of logic because for all models M, the intended models of D, the diagram of M, agree on the truth of the formula phi we're interested in. In fact, I'll try to actually be quick here and let Eric start, because we might... Eric, you should go ahead. So, what Eric is now going to do is define this generalized notion of logical consequence and basically tell you how you can extend the notion of prologue to come up with rich prologue, which not only allows you to answer standard queries like there exists x p of x, but it also allows you to do sigma 2 queries and pi 1 queries. And go ahead, do you want this? Yes. Yeah. Thanks. Oops.
25 minutes. Well, in that case, I will probably skip that. And just show you what is the general picture of our framework. Okay. So basically what we do is pick up a set of parameters. We have seen 3 parameters: vocabulary, possible words, possible evidence. Adding a few other parameters, we get what we call a paradigm, which is a generalized logic. So classical logic is just an instance of this set of class of paradigms. Okay? When you set the parameters to some values, for instance, W to all structures, possible evidence to empty set, etc., you get classical logic. So these paradigms define a notion of generalized logical consequence. We have seen this notion on with these 4 examples. Okay? These 4 examples are particular cases of this generalized notion. This notion of logical consequence, generalized logical consequence, is more complex than the classical notion of logical consequence. For classical logic, everything we have a compactness theorem. So everything that is a logical consequence of a theory is actually a deductive consequence of a theory, or the finite subset of a theory. So all the hierarchies somehow collapse to the level of deduction. On the other hand, when the paradigm here is a bit more complex, what you have is a whole hierarchy of generalized logical consequences. So the first level corresponds to the level of deduction, and then you have induction, and then something more complex which corresponds to learnability in the limit, and then it's more and more complex. Okay, so this is basically the general picture, having classical logic as a particular instance of this general framework. So what we want to see is how we can basically lift classical logic, proof theory of classical logic, and prologue, an application of this proof theory, to our framework. So generalize the notion of proof and generalize prologue and get a system which is able of performing more than just deductive consequences. Okay, so I will basically now spend time on explaining which prologue. So prologue plays one of the games we have seen. So prologue tries to discover whether a logical formula phi follows from a theory T, but there are some strong constraints on that. First, you have to assume that W is the class of all structures. T, the theory you start from, cannot be arbitrary. It has to consist of rules. So this means of formulas of the form for all universal formulas. Then the conjunction of atomic formulas implied an atomic formula. Okay, so very restricted class of starting points of theories. And the formula phi you want to prove also has to be very special. It has to be a sigma 1 query. So it has to be an existential formula whose body is a conjunction of atomic formulas. Okay. So prologue plays this game. Now there is another interpretation of prologue in terms of another game. We can actually claim that prologue plays the game where W is the class of Hebron structures. Okay, not all structures, but just Hebron structures. And E consists of all atomic sentences. So the evidence that you can get is just atomic sentences. T is a finite set of rules, and phi is the sigma 1 query. So we have this equivalence between both interpretations because of the restricted nature of T and phi. Now, if you are interested in more complex kind of queries in universal formulas or in sigma 2 formulas, then you cannot take for W all Hebron structures. Okay? So the equivalence holds either Hebron structures or all structures because of the very restricted nature of T and phi. So you know that the point of these slides is just to make the parallel between prologue and which prologue. Remember, we want to lift prologue to which prologue. So basically, I remind you of how Prolog works, and then we see how which Prolog generalizes this, the mechanism. So Prolog's computations are actually a side effect of a deductive consequence. So in order to win the game, T implies a query, a sigma 1 formula, means that Prolog has to find a sequence of terms that can be substituted to X and yield a formula, psi, T substituted by X, which is quantifier-free and which follows from T. Okay? And we're actually interested in this side effect. We pretend that we don't know whether T implies the query, but we know that actually T implies the query, and we're interested in the side effect, in the result of this computation. And we'll see that it will be the same for which Prolog. It will also be a side effect. So, for instance, the previous games could be cast in, could yield very simple programs such as this one, or basically you say that before is reflexive. You say that if X is a predecessor of Y, then X is before Y, and you express the transitivity relation with the third clause. So this is the background knowledge, right? Then you have a finite set of facts. So here the evidence is the set of atomic sentences. And you ask a sigma 1 query. So does there exist an X such that these three, does there exist an X, a Y, and a Z such that the formula holds? So basically, you pretend that you don't know that 0 is the minimum element. Okay, so that you ask this query, and the result of the computation is, of course, instances of X, Y, and Z that satisfy this query. Okay, so this is the first solution you get when you run this program, and then you get other solutions on backtracking. Okay. So which Prolog can play these games? Which Prolog is an extension of Prolog? So it can exactly do the same, play the same kind of game as Prolog. But it can also play games of the form T implies phi, where W is the class of Hermann structures, same thing as the second interpretation. E is a set of atomic or basic sentences, which means that the evidence basically corresponds to raw facts, either positive or negative. And the theory consists of two parts, the background knowledge plus the set of all evidence true in the underlying world. And more, the main point is the query. Okay? What is really marginable for which Prolog is that the query is not sigma 1 but sigma 2. Okay? There exists such that for all there exists X for all Y, and then a quantifier-free formula. So for Prolog, you could take for W either all structures or all Hermann structures, because you are playing with sigma 1 queries. With sigma 2 queries, you cannot take for W all structures. It has to be all Hermann structures. So, which Prolog's computations are a side effect of an inductive inference followed by a deductive consequence, inductive inference. Okay, the idea is that if you want to prove a sigma 1 formula, you make a deduction, a pi 1 formula, you make an induction, and a sigma 2 formula will first induce a pi 1 formula, and from this formula deduce the sigma 2 formula you are interested in. So in order to win this game, you see it's quite parallel to what happens in Prolog. Win this game means find a sequence of terms that, substituted to X in the query, yields a pi 1 formula which follows from T. So let's look at an example of a program in which Prolog, where we can use exactly the same background knowledge as before. We use the same background knowledge. But now the set of facts is potentially infinite. In Prolog it has to be finite. In which Prolog it's one finite subset of the potentially infinite set of data which are true in the underlying world. You see, you need infinitely many formulas to describe this infinite order. And you can does find me an x such that x is before y for all y, or x is after z for all z. So basically find me an x which is either a minimum element or a maximum element. So once again, you pretend that you don't know the answer. Of course you know that the answer is correct, since you choose the application is an order which has either a least element or a largest element. But proving this fact, proving the sigma 2 sentence, yields basically as a side effect the result of the computation, a value of x of the existentially quantified variable that satisfies this for all formula. See? So this cannot be expressed naturally in Prolog, okay? Because this is something that cannot be discovered conclusively with certainty. It can just be discovered in the limit. So if you have just a very limited number of facts, the output might be wrong. But as soon as you get enough facts, then the output is correct and you will stabilize to this output. So what is Rich Prolog's general strategy? There are two stages. The first stage is to find a witness for the query, the sigma 1 query, obtained from the sigma 2 query by replacing for all y by the exist y. Okay, so basically you try to find a common witness to all these existential queries. So the problem is, how do you choose these terms T1, Tn? Okay, basically you want to show that x psi holds for some x and for all y, we'll basically find an x which holds for some y's. So you have to choose some closed terms T1, Tn and find a common witness to that. And then you make the inductive leap. If you have shown that some instant of x satisfies these n queries, you will make the inductive leap, so you will conjecture that for all y, psi of Ty holds. Okay? So you generalize, you make a big generalization from just a finite set of closed terms to a potentially infinite set. So you need to confirm that. We know that we cannot learn with certainty. We can just converge to the limit. So the only thing we can do is, if we are wrong, we should be able to refute this statement. Okay? So we try to refute this statement. So refute this statement means try to prove the negation. And the negation is a sigma 1 query. So if we cannot refute this sentence, if we cannot prove this formula, then we will basically stick to our assumption that this universal formula holds and basically output the result T. We will output T, the witness found during stage 1. On the other hand, if we show that this holds, so if we refute our conjecture here, then we backtrack to stage 1 and we look for another witness. So the previous example was a query of this form. Now you will tell in Prolog we don't have disjunction. Okay? A sigma 1 query is existential quantifier followed by a conjunction of atomic formulas. So here we have a disjunction of atomic formulas. Well, it's not very hard to transform this query into a query whose body is atomic. We just have to add two clauses to the program. Okay? Basically, if we want to answer this query, we have to find an x which is before y, or an x which is after z for all y for all z. Okay? So when we have a disjunction here, we can replace this query by a simple query at the cost of introducing two new clauses in the program. So this technique can be generalized to any kind of sigma 2 query. Basically, assume that you have a query of this form where you have many occurrences of conjunction, disjunction, and negation. So you see that this query consists of a conjunction of two subformulas. The first formula is atomic, and the second formula is more complex. So what you will do is introduce a new predicate symbol okay, to represent this node. Now the second subformula of the query is a disjunction, okay, with two disjuncts. The first disjunct is the negation of P2 of Z, and the second disjunct is a big formula that will be represented by Q3. This last formula is a conjunction of three terms, P3 of XY, P4 of Y, and finally a disjunction of two subformulas. Okay, so if we draw the path tree of this formula, if we introduce new predicate symbols at every node, then we can transform this query into a very simple query, sigma 2 query with an atomic body. We just have to add 1, 2, 3, 4 different clauses to our program. Okay, so we basically introduce a new predicate symbol Q1. So this complex query becomes this very simple query. To get what we want, we just need to add all these clauses. See, so Q1 says that to satisfy Q1, you have to satisfy P1 and something that will be represented by Q2. So this is expressed here. To satisfy Q1, you have to satisfy P1 and something represented by Q2. And to satisfy Q2, you look at the path tree, you have Q2 corresponds to disjunction, hence you will introduce two clauses, one for each disjunct, and so on. So let's get back to the previous example, so to look a bit more carefully at how things work. So remember that we want to solve this query. We want to find a witness X that will satisfy this formula. So we have to solve this query. Okay, we have to substitute Y and Z by closed terms and find a possible witness X that will satisfy this formula before we make the inductive leap. So there are two techniques. This is the simple technique where we substitute Y and Z by a closed term. What we might want to do is to be a bit more general and try to target these closed terms. So come to try with more general formulas where 0 will be an instance of the query we want to solve. But these are technical details. So the basic idea is basically try to solve this query not for all Y, not for all Z, but for some instances of Y and Z. So for instance, it might be those ones. So assume that we have found a possible witness. Assume that X equal to Y, X equal to 1 is the result of this computation, of this query. Then we make the inductive leap. So basically what we do is assume that 1 is before Y for all Y, or 1 is after Z for all Z. So this is the inductive leap. Then we have to confirm this conjecture. So we try to prove the negation. We try to refute this hypothesis. So we try to prove this formula. Now here we have a problem because we have negation. The evidence we have is formulas of the form before MN, not before MN. This will never be given by the structure. Well, in this case it's very easy because we have the total order, which means that for all structure, if X is not before Y, it means that Y is before X. So we don't have negative data explicitly, but we have them implicitly. Okay? Adding negative data would just be redundant. Okay? Because if we get before NN, we can immediately conclude that not before MN. Hence, we have the negative data implicitly. So what we can do is basically replace the refuting sentence in which we had not before 1 Y but before y1. Okay, so here we use the background knowledge. But it turns out that in many applications we can use this technique, we can remove negation using an equivalent formula. And if this is not the case, we have to use other techniques, but we won't address these techniques here. So you see, at the end of the first stage, we basically guess this formula, try to refute it, and if we find a refutation, if we find a counterexample to that, then we backtrack to the first stage and try to find another witness. So what the theory says is that in the limit, we converge to the right output. So in the limit, we'll discover what is the minimum or maximum element of our ordering. So let's say a few words about inductive logic programming, because this kind of issues has been addressed by inductive logic programming. So let's look at how things are described in this field. Well, ILP is described as follows. Given some background knowledge, dk, and given a set X of possible evidence of data, the aim is to find a logic program T that implies every datum that has been observed and does not imply any possible evidence that hasn't been observed. Okay, this is how ILP is described. Find a logic program that, together with the background knowledge, generates all the data that have been observed and no data that hasn't been observed. So, inductive logic programming, for instance, yes, here is an example. So if we have a set of possible evidence given by this set X, then we can basically come up with a logic program of this form. First, 0 is a predecessor of 1, 1 is a predecessor of 3, and then you see you have a kind of regularity, because you say that 0 is before 1, 1 predecessor of 3, 3 predecessor of 2, 2 of 4, 4 of 5. So we have a common pattern here that is repeated again and again. So we can write a few rules that will basically capture this pattern. So 3 is a predecessor of 2, when 1, 0 is a predecessor of 1, and 1 is a predecessor of 3. And this will hold for not only 0, 1, 3, 2, but also numbers, all these numbers, plus 4, plus 8, plus 12, etc. Okay, so this structure here can be expressed by a few rules. So this is how ILP works. Given some set of possible evidence, given some background knowledge, find a logic program, set of rules that will generate precisely this set X and nothing more. Well, so it consists of induction as the inverse of deduction. Okay, the problem is given X, given some background knowledge and X, find T, using the classical notion of logical consequence. Okay, so you have to inverse this relation here. Phi is what you have, and T is what you want to get. So it's reversing this relation. So in our view, induction is not the inverse of deduction. Deduction and induction are particular cases of a more general notion of logical consequence. So instead of formulating the problem as find T such that background knowledge union T implies the data, so inverse this relation, we formulate the problem as find T such that background knowledge plus data imply in the logical sense, but extended, T. Okay, the problem is to perform a generalized logical consequence. Okay, so what you have is on the left-hand side, and what you want is on the right-hand side. So it's not inversing classical logic, it's making a more complex logical inference. Now, for the previous examples, the formula we want to prove is given. Okay? All the games involved were based on some set of possible worlds, background knowledge plus the target formula we want to discover. The formula was given, whereas here, T, the logic program, is not known, it's what we want to know. So, of course, we have to make this logical inference, but with an unknown formula. So we cannot exactly use this framework, we have to adapt it a bit. So what we can do is, instead of formulating the problem this way, we can actually write a sigma-true query which will take care of all the conditions on T. T has to imply all positive data and nothing more. This hasn't been captured by this formulation. It's captured by the sigma-true formula. We basically say that we want to find the logic program pi, such that for all data D, the logic program pi generates T if and only if D is one of the observed data. So now this is fine, because this formula has to be a logical consequence of background knowledge plus data. And when we run which prologue, when we try to solve this query, when we try to prove that this formula is true, what we get as a side effect is a term, a closed term T, that will satisfy this formula while T substitutes pi. So it's a term that represents the logic program we want to learn. Okay? So first we express things in terms of a generalized notion of logical consequence, and then we write some conditions on the logic program we want to learn. We can express this condition in terms of a sigma-true query. And the result of the computation is a term that represents this logic program we want to learn. So, conclusion, well, our aim here was to show that we could have a unified, coherent framework which would encompass classical logic, induction, plus learning paradigms. All these things somehow are particular cases of a more general notion of logical consequence. Now, the ideal of declarative programming can be extended to a system that can work in deductive mode. When you try to answer sigma 1 queries, you are in deductive mode, you try to make a deductive inference. And what you get is a certain answer. You just need some finite evidence, find background knowledge, and at some point you get an answer which is true. So this is prologue. This is deduction. Now this system can also work in inductive mode. In that case, it will usually try to answer a pi 1 query. So in that case, there is no conclusive conclusion. We can just converge in the limit, and you will know that if you are wrong, you will be refuted with certainty. It's certain refutation. So this system can do that when it is in inductive mode. But the more interesting use of the system is when it is in learning mode. So when it tries to solve the sigma-true query. In this case, it will try to make an inductive leap from a deduction. It's a backtrack search, so starting from level sigma-2 backwards, and the result of the computation represents what you want to learn. Okay, so I think we are done.
Okay.
Yes.
Thank you very much. I've got a very quick question. I'm sure you must have been asked this question a few times. What happens if you, say, have inconsistent instances? Say, for instance, if some of these observations are simply incorrect.
Yes, here it's based on the assumption that the world gives you data. So how can data be inconsistent if they come from the world? They are results of observations, results of experiments, so they have to be consistent. Otherwise, what we have to do is basically work with models that introduce some kind of noise.
Yeah, that's what I mean.
Yes. Well, it's just an instance equivalent paradigms. Yeah.
The initial learning model, the noisy version of these theories are still not there.
So, you think it could be a change?
Oh, it will have to introduce heuristics.
Okay.
So it can be modeled. It hasn't been done. Right now, we're just trying to assume that if the world behaves perfectly, and
very much again. The slides at the top again will